So in the last video, we talked about the definite integral, where we had a function whose graph was entirely above the x-axis on the interval that we're concerned about. So, for instance, if I have the function f of x and I have a curve y equals f of x, and I have two values, x equals a and x equals b, then the integral from a to b of f of x dx, what that means is the area under this curve, f of x, between x equals a and x equals b. It's this area right there, the area underneath the curve above the x-axis between x equals a and x equals b. And we know exactly how to find that, or at least in principle we do. We take this interval AB and chop it up into little pieces, and on each piece we'll construct a rectangle, and the area of that rectangle is the width of that rectangle times the height of the rectangle, which is the same as the height of the curve at some point in that rectangle. And we multiply that together, we add up the areas of all the rectangles, and we let the number of rectangles go to infinity, and the widest rectangle gets narrower and narrower as there are more and more rectangles. So I want to ask a question now. What if the function f is not positive or 0 on AB? What happens if there's part or all of the interval where it's negative? Well, let's say we have a curve that looks like this. And I'll put x equals a over here and x equals b over here. Now we can certainly take this interval AB and chop it up into little bits. And on each one of these little bits, on each one of these little subintervals of AB, we can construct a rectangle which touches the curve. Doesn't matter exactly how we do it, as long as the rectangle touches the curve somewhere inside that rectangle. Now, the area of this rectangle is going to be the width of the rectangle times the height of the curve wherever we choose to have the rectangle touch the curve. The area of this rectangle is going to be the width of this rectangle times the height of the curve wherever we choose to have the rectangle touch the curve. Look what happens over in this region. On this little region, let's say we have the rectangle touch the curve over here. We have the width of the rectangle, and then the height of the curve there is negative. So if we're going to take the width of the rectangle and multiply by the height of the curve, we're going to end up with a positive number times a negative number. And so it turns out that the area of this rectangle is going to count as negative. Same with this rectangle over here, it's going to count as negative. And the practical upshot is that when we're computing the area under the curve, stuff above the x-axis counts as positive area. And stuff below the x-axis counts as negative area. So what we're talking about is a more general concept of area. We're talking about something called signed area. Signed like positive or negative. Stuff above the x-axis counts as positive area. Stuff below the x-axis counts as negative area. So if we have a more general function, we can't just say it's the area under the curve above the x-axis. Some of it might not be above the x-axis. So in general, the integral from a to b of f of x dx means the signed area enclosed between y equals f of x and the x-axis. That's still true over here. The x-axis is still the boundary. Over here it's the boundary below, and over here it's the boundary above, between x equals a and x equals b. And just as before, there are some situations where we can easily compute the derivative. The definite integral. So for instance, let's say I go between -1 and 2 of x dx. So I want my definite integral of x dx between x equals -1 and x equals 2. Let's go ahead and draw ourselves a picture. Again, we know what y equals x looks like. It's the curve going uphill at 45 degrees. Let's put x equals 1, x equals 2. Of course, this goes to height 2, and x equals -1 over here. That's at height -1. So we want this area right here. This signed area right there. Some of this is going to count as positive because it's above the x-axis. Some of it's going to count as negative because it's below the x-axis. So let's figure out the area of this part above the x-axis. Well, again, we just know the area of triangles. The base is 2, the height is 2, and the area of a triangle is 1/2 base times height, 1/2 2 times 2, which the area of that whole triangle is 2. And the area of this triangle is 1/2 base times height. So 1 times 1, so that's 1/2. But it counts as negative. So this part counts as positive, this part counts as negative. So the signed area is the area of this part, 2, plus -1/2. In other words, 2 minus 1/2, or 1/2. So when you're computing the area of the signed area, in other words, computing the definite integral, you take all the positive stuff and subtract off all the negative stuff. Let's do another one. Let's say I ask you for the definite integral between x equals -pi and x equals pi of sine x dx. So we know what the sine curve looks like. So let's say here's pi, here's 2 pi, here's -pi. So the sine curve goes up, goes down. Well, that's pretty sad looking. Try that again. There we go. And I'm asking you to go between -pi and pi. So at this point, you actually have no way. If I had asked you to go between 0 and pi, you have no way of knowing how big that bump is. You have no way of knowing that area. You can make some estimates. After all, you can see that this rectangle right here has height 1 and width pi. So that whole rectangle has area pi. But you don't know how big this bump is. It looks like it's a half, maybe a bit more than a half of it. More than half. But you don't know what it is. But one thing you can tell is that this bump and this bump have the same area. This upside down bump have the same area as this right side up bump. And so whatever the area of this is, since this counts as negative, you're just going to take this and subtract it off from that, and they have the same area. So what are you going to get? 0. So again, we can use a little bit of geometry to be able to work out some of these definite integrals without going through the process of breaking everything up into little bits and computing it, and then taking the limit as the number of rectangles goes to infinity and the widest rectangle gets very narrow.